Hello students, welcome to Microwave Engineering Laboratory, and today's experiment is, let's see here. So these are the list of experiments, okay? So I already explained, and these are the 12 experiments we have to perform in the laboratory. And today, directional coupler characteristics. Let's learn about the directional coupler characteristics. Okay. The aim of the experiment is to study the function of a multi-hole directional coupler by measuring coupling factor and directivity of coupler. Okay. Yeah. The required apparatus is microwave source with a klystron tube, isolator, frequency meter, variable attenuator, multi-hole directional coupler, tunable probe, and detector mount, matched determination, waveguide stands, CRO, cooling fan, and klystron power supply. So these are the required apparatus required to perform the directional coupler experiment. And next, let's see the block diagram. Coming to the block diagram, the first one is microwave source. You know that the source is connected to the tube, okay, microwave klystron tube. Then klystron tube to the isolator, isolator to variable attenuator, then variable attenuator to frequency meter to MHD coupler. I mean multi-hole directional coupler to matched load, and matched load to the detector mount, and detector mount to CRO. So this is what the required test bench to perform to do the directional coupler experiment in the laboratory. So initially there is a klystron power supply. Power supply has a different knobs, I mean incorporated with the different knobs, and those are biasing voltage knob, rippler voltage knob, and display section and modulation knobs. So by rotating the bias voltage knob, you have to fix the voltage in between 230 to 240 volts. Then after, find out the beam current. Then by rotating the rippler voltage knob in anti-clockwise direction, you have to fix the maximum signal strength at CRO. You can use the CRO, otherwise VSWR meter also. If you use the VSWR meter, we can find out the power directly. If you go for the CRO, so you have to calculate the voltage, then based on the voltage, by using the voltage, then you have to perform the 20 log operation, then we can find out the power values. Okay, and now, yeah, let me show the directional coupler diagram. See here, so directional coupler has a 4 ports, port 1, port 2, and port 3, and one port is, okay, it is a matched termination, completely isolated. Okay, connect the port 1 to the frequency meter, and port 2 is connected to the detector mount, and port 3 is connected to a load. Okay, so whatever the signal passes through the waveguide reaches the frequency meter, and that used to passes towards to the directional coupler, and you can take the output at port 2, okay, by applying a load at auxiliary port or port 3. Okay, when the energy is transmitting or transporting towards to the directional coupler, here there is a small operation will happen. So the power which is passing through, some amount of energy or microwave energy which passes towards to the port 3 also, that purely depends upon what type of coupler you are using here. By suppose if you use the 3 dB coupler here at auxiliary port, and the amount of energy which leaks towards to the port 3 is a 50%. Okay, and if you go for the 10 dB coupler or 6 dB coupler, the power splitting ratio purely depends upon the whatever the coupler, what type of coupler we are incorporated to the auxiliary output side. Okay, at port number 3. Just remember that point. Let me show you the directional coupler to you guys. Yeah, guys, you see. So this is what the see guys. So this is what the directional coupler we are using in the laboratory. So hopefully, yeah. Check it here. So this is a one port. Okay, port 1, port 2, and port 3. So these are the 3 ports, and other port is completely isolated or matched terminated. Okay, so 1, 2, 3, and 4. This is how each look like. Got it right? Go to the observations. You have to find out input voltage, beam voltage, rippler voltage, and beam current. Okay, I already told no. So input voltage you can find out on CRO. Okay, by calculating the amplitude value, we can find out the input voltage. Then beam voltage should be 230 to 240. Rippler voltage that nearly minus 2012 to 203. Okay, beam current, it should not exceed the 18 milliamps. You go to the tabular form, see here. So yeah, input voltage at port 1 and output voltage at other 2 ports, port 2 and port 3. Here port 4 is completely isolated. So if you check the value at input voltage, if you connect the port 1 to the input side, okay, you can check the values at port 2 and port 3 by applying the load. If you apply load at port 3, you can calculate the power at port 2 by using the detector mount. So vice versa. Like that, you have to perform the experiment. Let's go for the calculations. Okay. Here, the isolation in dVs, which is equal to 10 log of P1 to P2. I told you if it is a power values, okay, power values, you have to perform the formula with the 10 log of P1 to P2. If it is in voltage, 20 log P1 to P2. Then coupling coefficient, 10 log of P1 to P3. If it is in voltage, 20 log of V1 to V3, and directivity 10 log of P3 in forward direction. I mean power in forward direction to power in reverse direction. So which is equal to 20 log of voltage value, whatever we find in the forward direction, to voltage whatever you find in the laboratory, V3 in reverse direction. And we know the formula, isolation equal to coupling coefficient plus directivity. You have to check it. This formula is satisfied or not in the laboratory. And coming to the Viva question. So here I have raised some of the questions. Just go through the questions and try to answer these questions. And the first question is, what is the primary purpose of the directional coupler? And second question, how far apart the two holes in the simple directional coupler? And question number 3, what is the purpose of absorbent material in the directional coupler? Question number 4, in a directional coupler that is designed to sample the incident energy, what happens to the two portions of the wavefront when they arrive at the pickup probe? Okay, you have to justify this one. Just read it carefully and try to answer this question. So this is a most important question. So based on this question only, so we are doing the experiment in the lab. Then question number 5, what happens to the reflected energy that enters to a directional coupler that is designed to sample a incident energy? Okay, so these are the 5 questions I have raised here, the most important questions in the exam point of view also. So kindly try to answer these questions. Okay, and let's move to the laboratory and we'll see the we'll do the experiment practically and come back, and I'll explain the theoretical calculations on board. Thank you. Thank you so much.
Good morning, students. Welcome back to the microwave engineering laboratory, and today's experiment is directional coupler. See here, whenever you are in the laboratory, make sure about first initially switch on the cooling fan and just keep an eye that airflow towards to the Klystron mount, because it is a high power generator. So just check it, the airflow towards to the Klystron mount or not. Then after, just switch on the Klystron power supply, and here select the AM mode, and by rotating the bias voltage knob, make sure beam voltage should be 232 in between 240. It should not exceed 240. Then find out the current, corresponding current, that should not exceed 18 milliamps, and rippler voltage, by rotating the rippler knob in anti-clockwise direction, fix the maximum signal strength appears on CRO. Okay. Now see the test bench for the directional coupler. Here Klystron power supply is connected to the mount, and it is connected to the isolator. Here isolator works like a uniline, which allows only the power in only in one direction. Next, it is connected to the variable attenuator to frequency meter to detector. So step number 1, you have to find out the maximum signal strength, I mean output, by using the detector mount. So this is what the step number 1. Step number 2, so take off the detector mount and connect the directional coupler. See here, so there are 4 ports. Port number 1, port number 2, port number 3, and port number 4. So it is terminated, isolated one. And if you connect port number 1 to frequency meter, okay, and port 2 to the detector mount, and port 3 matched termination. So like that you have to take the values, okay, and change the preferences, I mean make it a reverse, like a port 1 and port 2 connections, and again repeat the same procedure. Let's connect the port 1 to the frequency meter, and we'll take the value.
345.
See here, so directional coupler, port 1 is connected to the frequency meter. We are taking the output at port number 2 by using the detector mount, and port 3 is connected to a matched termination. So this is how you have to take the values. So input at port 1, output at port 2. Okay, port 3 is completely blocked. See the signal here. Now, ma'am, could you change the port preferences? Connect the matched termination to the port 2 and take the output at port 3. Yeah. Definitely port 3 values are 0. Small. See here, the power is, I mean, just to see the signal strength, it's very, very low. Now, you have to change the, I mean, disconnect the directional coupler, and port 2 connected to the frequency meter, and take the output at port 1, and as it is port 3 as a connect the port 2 to matched load. So like this you have to do the experiment and write down the values, and you have to perform the you have to calculate the isolation. So isolation equal to 10 log of P1 by P2. So if you know the power values straight away, you can use this formula 10 log of P1 by P2. Otherwise, we are using the CRO, right? We are taking the amplitude values. So I mean voltage. For that, you have to use the formula 20 log of V1 to V2. By using that one, we can calculate the isolation. The next coupling coefficient. For coupling coefficient, the formula is 10 log of P1 to P3. Okay. But here we are taking the voltage, no? That is a 20 log to V1 to V3. The directivity value 10 log of power at port 3 in the forward direction to power at port 3 in the reverse direction. So by performing that one, so you will get the directivity. And in terms of voltage, that is 20 log of V3, voltage at port 3 in a forward direction to voltage at port 3 in the reverse direction. So finally we know isolation equal to coupling coefficient plus directivity. So you have to prove this one, and this is how you have to perform the experiment in the laboratory. Thank you so much. Let's see directional coupler characteristics now. Students, see here. So whatever we found practically in laboratory, the input voltage is 10 millivolts and beam voltage is 240 volts. Repellor voltage is minus 203 volts. Here minus sign because it is a repellor voltage. A voltage we are considering in reverse direction, and beam current 18 milliamps, that should not exceed 18 milliamps. Remember this one. This value should not exceed 18 milliamps. Let's come into the tabular form. Input voltage, and you have to take the readings at two ports. Output voltage. See this one, directional coupler, no? So if you consider, so port number 1, port number 2 and port number 3. If you apply input at port number 1, you have to take the output at two ports, port number 2 and port number 3. So that's why see the tabular column, input voltage at particular port, output voltage at two ports. Okay, if you apply input voltage at port number 1, so that value is V1. Okay, voltage at port number 1, V1 is equal to 10 millivolts, and output at port number 2, so V2 equal to 9 millivolts, and output at port number 3 in forward direction. Okay, so V3F, which is equal to 0.4 millivolts. Next, okay, just reverse it, and now port 1 behaving like a port 2, port 2 behaving like a port 1. So port 1, port 2, port 3 as it is. Now, so just check it. So voltage at V2 10 millivolts, V3 reverse direction 0.2 millivolts, and voltage at V1, port 1 is 0 millivolts. So now we have taken these values practically. So by using these values, I have to calculate first of all isolation in dBs. So we know the formula 10 log of P2 by P3R, because it is a 10 log. Power values we can calculate by using the voltage standing wave ratio meter, VSWR meter, but here in this experiment we are using CRO, right? That's why I have taken the voltage. You have to use the voltages, right, to calculate the isolation. For that purpose, I am taking the formula 20 log of V2 by V3 in reverse direction. So you will get the value 33.97. Okay, 33.97. Coming to the coupling coefficient, in terms of power, 10 log of P1 by P3. But if you go for the voltage, in case of voltage, 20 log of V1 by V3 in reverse direction, and that value you will get 27.95. But we know the formula. So I is equal to C plus D, right? So isolation equal to coupling coefficient plus directivity. For that purpose, again we have to perform the directivity. So calculate the directivity equal to 10 log of P3 power at port 3 in forward direction to power at port 3 in reverse direction. So we have the voltage values, right? So in terms of voltage, that is a 20 log V3 in forward direction by V3 in the reverse direction. That value will get 6.02. So now we know the formula. Isolation equal to coupling coefficient plus directivity, right? So simply substitute those values. So I equal to C value, coupling coefficient we got the value 27.95 plus directivity value is 6.02. By substituting these two values in the given formula, then answer is 33.95. Just cross check it. So 33.95. On what we got the isolation here, 33.97. Just only a small minute change is there. So 33.97, 33.95. So both are equal only. So whatever the experiment we have done is perfectly we got the values. Okay. So this is how we have to perform the experiment in the laboratory, and that too directional coupler characteristics. Thank you so much.